Morning, afternoon, or evening, physics people. This is day 5 in physics, unit 3 fields. And we're looking at electric fields today. Okay, first 4 days, well, except the first day, we looked at a little bit of electric field lines between charges, diagrams of that. But in the second, third, and fourth days, we were looking at the electric force created by uh, charged objects, Coulomb's law particularly, and how to charge objects by induction and contact. Today we're going to go into just the electric fields part. So electric fields, we're going to look at two areas. I don't think it's going to be a very really long class. We'll see. I don't think it'll be too long, because there's only two main areas we want to look at. Okay, so let's set our blackboard up here and kind of talk about what we are going to do in this area of electric fields. So this is day 5. Unit 3. And we're going to be looking at electric fields. Okay. And we're going to be basically, we're going to define that, obviously. The other thing we're going to be looking at is we're going to look at finding strengths. Of electric fields. And we use positive test charges for that. And then we're going to be looking at finding electric fields around a point charge, strengths of that. Or we'll say combining electric fields and Coulomb's law, because that's what we're really going to do. These are not really hard mathematical concepts, so it shouldn't be too hard for us. There we go. Coulombs. So those are the three things we're going to do here, and it shouldn't take us, it should probably take us about 35, 40 minutes to do, so it shouldn't be too hard. The mathematical problems are not that difficult in terms that we're just doing some simple dividing and multiplying, and the equations are not that loaded with variables, so they shouldn't be too hard for us to do. So the first thing we're going to do is we're going to look at electric field. What is an electric field? And we're also going to look at electric field equation, the strength equation. And of course, the force that is created by an electric field is a vector quantity, because we know that forces are vectors. So we have to keep in mind that we need a direction when we're talking about electric field forces, okay? So an electric field strength is basically measured as a force per amount of charge. Okay, so it's kind of a rate. So let's start off with an electric field. Electric fields produce forces in an area based on electric charges, or two or more electric charges. Okay, so if we remember day 1, the diagrams of electric field lines. Between charges. Okay? And just to remind us of what they look like, if you have a positive charge, a point positive charge, uh, all of the electric field lines go in towards the positive charge. It's there. They all point in. If you have just a negative charge, or sorry, I got that wrong. They all point out. Positive. I got that wrong. So I'm looking at my diagram and I read it wrong. Positive charges, they all point out from the positive charge, right? And then a negative charge, they all point in. So kind of like this. I better just draw it so that you remember. Okay, so if we had a positive charge, right there, the electric field lines would point out like this in a spread out symmetrical pattern. If we had a negative charge, they kind of point in. Okay, and then we also drew diagrams of two charges apart and stuff like that. So we also did that as well. That's included there as well. So don't forget that part as well, but you can look back and see that. Just a little reminder. Okay, so we're going to talk about an electric field strength first of all. And that's the very first area that we're going to look at, and we're going to look at equations here. So an electric field strength we spell field wrong here. Okay, an electric field strength is measured as a force amount, we'll say, per unit of charge. So if we're talking about the unit that we're going to get newtons per coulomb, because charge is measured in coulombs and force is measured in newtons. So we're going to have a newtons per coulomb rate. So how much force per unit of charge do you have? That's what a field strength gives us. Okay, and how we find an electric field strength is it is basically calculated by testing how much force you have on a positive test charge. Okay, so electric field strengths are calculated by measuring, or found if you like, the force that is on a positive, always a positive, test charge. So you take, if you have an electric field that's being generated, usually it's between, two objects or two plane plates or something like that, and you want to find out how strong it is, you put a positive test charge in there, and you see how much force it experiences. Okay, and we'll talk about Millikan's oil drop experiment, how he did that later on. And then that way you can calculate the electric field strength that you have. Okay, so it's basically measuring that force and then dividing that force by how big the test charge is. Okay, so it's basically just a 3 variable type equation. So what does it look like in terms of an equation? It looks something like this. Okay. E, which we'll use a capital E, don't get mixed up with energy now, because it's not energy, it's electric field. So we'll use an E that's big like that. And that's equal to force, which is a vector, so I'm going to put a little arrow over top of it, on Q prime, okay, over Q prime. So we use Q prime to represent the positive test charge. So what are each of these? Okay, the top here, let's change colors here. Okay, the top here is the force on the test charge measured in newtons. Remember, there has to be a direction with force as well. Newtons, okay? And then, of course, Q prime represents the test charge. Okay, this is the charge size of the test charge. Okay, the size of the test charge. Okay, and that's measured in coulombs. So that's where we get our newtons over coulombs. And this represents the electric field strength that's generated. Strength of the electric field. Right there. And that's going to be measured in newtons per coulomb based on what we have over here, right? Okay. And remember, as we set up here, Q prime is always positive. Okay, it's a test charge. What we call it. It can be different sizes, but it always has to be a positive one so that we know the direction of the electric field when we're doing it. We always have to know what that size is. Okay, so let's basically, it's pretty straightforward equation. So let's just look at a couple of simple examples. Calculating the electric field, calculating the test charge, calculating the force, those kinds of things. Okay, so we'll do a couple examples of that over on the next page here. I'll just throw up an example section here. Okay, so let's say we have, let's say a force of 0.36 newtons. Right, now, some people might be asking, oh, well, what, how much is a normal electric field strength? And what are some typical electric field strengths? Well, if you're thinking about taking a charged rod and you hold it close to near a positive test charge, right? So if you take a charged rod like one of these rods here, like a hard lucite rod, like one of these things, and charge it up using fur or something like that, and you hold it close, like really close, like a centimeter away from a test charge, you're going to see about 1,000 newtons per coulomb. Remember, a coulomb is really big, right? Because we measure charge in microcoulombs. Okay. If you want to see a spark in air when you see those cracks when you walk across the rug and you touch like metal, okay, that charge has to be around 3 million, okay, newtons per coulomb to get that electric field little zap. Okay, and if you want to look at it, the charge of an electron orbiting around a nucleus in an atom. We're talking like 1 times 10 to the 11 or 12 newtons per coulomb. It's quite a big electrical force, okay, electrical field. Okay, so that gives you an idea of some electrical field strengths. So let's go back to our practice here. So a force of 0.36 newtons, right, is experiencing oops, can't spell like that. There we go. or is experienced, not experiencing, by a test charge of positive, of course, 4.2 microcoulombs. Period. What is the electric field? Strength. This is nothing but a simple division for us. We know that our positive test charge here, Q prime, is this positive 4.2 times 10 to the negative 6 coulombs. Okay, this is in microcoulombs. So remember, micro is times 10 to the negative 6. Okay, and the force is to the right, 0.36 newtons right. Okay, and so when we do the electric field strength, that's simply our force of 0.63 newtons right divided by 4.2 times 10 to the negative 6 coulombs. Okay, so we should keep it in 3 significant figures. So you take your calculator out, 0.36 divided by 4.2, scientific notation, negative 6, and you get about 85,714. So if we round it off to 2 significant figures, it's about 86,000 newtons per coulomb, or as it's commonly written, they change it into kilonewtons, 86 kilonewtons per coulomb. Okay, so that's a pretty straightforward one, just using the straight division, finding the electric field strength. Of course, they can give you a field strength and a test charge, and you have to find the force that's there, that it's experiencing. So let's do one like that. Let's do the second one here. Let's say an electric field has a strength of, let's say, 12 kilonewtons per coulomb. Okay. If the test charge used is, let's say, 4.5, let's go millicoulombs. C like that means milli. Micro is a fancy U, so that means millicoulomb. Okay, so that's quite a big charge. It's 1,000 times bigger than a microcoulomb. What is the force on the charge? Okay, and they didn't put a direction on the electric field, so I should put a direction there. Let's put a direction. Let's say it's east. Always have a direction on your electric field. So let's say it's going to the east. Okay, so this one is just the same kind of question, but we're going to be doing some manipulation of it. Okay, so we should write our variables out first. We have the 12 kilonewtons should be written in per coulomb, should be written in newtons per coulomb, so that we can deal with that. But we can probably leave it as kilonewtons too, but just have to be careful with our units. But I'm going to put everything back to the original units. Okay, so our force is 12 kilonewtons east, which if we want, that would be 12,000 newtons per coulomb here. Per coulomb east. Okay. And our charge, test charge, is 4.5 millicoulombs, which we can write as 0. Well, let's write it in scientific notation since we've been using that for microcoulombs. Milli is 10 to the negative 3, so this is 4.5 times 10 to the negative 3 coulombs. Okay, so then if we take the formula, E equals force over the test charge. Okay, so and we want to find the force. So if we rearrange this, hang on, I'll put it on pause here. Okay, so just working on a problem there. So let's finish what we were doing. The force, okay, we put our coulombs up there. Or sorry, we're going to rearrange it for force. Force equals, so if we multiply these two together, right? Electric field times prime, Q prime to get force. So force is going to equal, that's what we have already. We want to find, or no, that's right. What am I doing? This is an electric field here, not force. Right, it should be a capital E. So let's fix that. There we go. I was correct there. So we're rearranging it for force. Okay, so then if we plug in our numbers, 12,000 newtons per coulomb east times 4.5 times 10 to the negative 3 coulombs. So that's why you could have left it in kilonewtons, because then your answer would have came out in kilonewtons, because the only thing that cancels out is the coulombs. So 12,000 divided by 4.5, scientific notation, negative 3. So you get about two significant figures. It's quite a bit of newtons. Oh, sorry, I divided there. What am I doing? Rusty day. It's Friday here today. I don't know what day you're watching this, but it's Friday for me. Times 4.5 Spellman 803. There we go. That's 54 newtons. That's better. Okay, so that's a way that we can work through looking at the electric field strength. So the other kind of area that we wanted to look at today, or I wanted to look at with you today, is what if you had a charge out there? Okay, what if you had a point charge and then a test charge around it? How can you find the electric field strength around a point charge? Well, you have to apply Coulomb's law, pardon me, as well. So that's our second area that we'll look at today. So this is our second area. We'll call it finding the electric field strength. Around a charged point. Okay, so if we have to combine the electric field strength and Coulomb's law at the same time, basically. Okay, so if we have, I'll draw out a diagram here to show you what we're going to be doing here. We'll derive this out. Will I expect you to derive it on an exam or anything like that? Probably not, because you'll get the equation on a formula sheet for both of the basic electric field strength and for the electric field. So if we have a charge, if we have a charge here, we'll call it Q, okay? And we have our electric, and we have our positive test charge, Q prime. And we want to get the electric field strength in between. We have some distance R in between them. Okay? We have two equations. We have the electric field around Q. That would be okay. That's the electric field around Q. And we have the electric force created between the two charges, which is this one. Okay, so we have Coulomb's law right there, and the electric field strength. So what we can do is we can take this and rearrange it for force, which we already did. So force equals the electric field times Q prime. Okay, and then we can plug it into here. Okay, we plug that whole expression here, EQ prime, into there, and then we can do some work. So plug it in there. Okay, and this cancels out, and we have an expression. Doesn't matter what the field strength is, okay, right? And we have an equation for electric fields around a charged point. This is the electric field strength around a charged point. Okay, you don't even need to worry about the size of the test charge, okay, because that cancels out on both sides. Okay. Okay, so if we have that, this is the electric field. Strength, but we'll just call it electric field because we know it's a strength. That's in newtons per coulomb. K is Coulomb's constant. Okay, that's at 9.0 times 10 to the 9 number, newtons per meter squared, coulomb squared. Q is the size of the point charge. Okay. And R is the distance between the test charge and the point charge, or the distance that you're away from that point charge, right? Wherever you are, if you're testing for the field strength. Okay, and we'll do an example of that. So this would be in meters, of course. This would be in coulombs, of course. Okay, and K is in, what is it in? It's in uh, uh, newtons per meter, or newtons times meter squared over coulomb squared. Okay, so let's do an example of this type of problem. And this will probably be where we'll stop today, as we're getting into 30 minutes here or so. So I don't want to go too much farther. We'll do an example or maybe two. Okay, so let's extend this out. Okay, so let's say we have what is the size of the electric field from a point charge if with a charge of, say, a negative 4.7 times 10 to the negative 5 coulombs. Ohms, 0.09 meters away from the charge. Well, let's make it 0.095 so we have two significant figures. Meters away from the charge. So if we do that one, we can take our equation. K Q over R squared, right? Okay, we know that K is a constant. So that's 9.0 times 10 to the 9 newtons times meters squared over coulomb squared. Q is this negative 4.7 times 10 to the negative 5 coulombs. And we're going to get this over 0.095 squared meters squared. So the meters squared are going to cancel out. And one of the coulombs is going to cancel out. So we're going to get newtons per coulomb when we work it out. So if we take our calculator out, 9 scientific notation, 9 times negative. Well, we don't really need the negative in there. We know that it's going to be attraction because the positive test charge is always positive. Okay, so negative charges go in, right, in towards the point charge. Okay, so then we multiply that by 4.7. If you leave the negative in there, that's fine. Scientific notation, negative 5. So that's 423,000. Okay, over 0.095 squared. Okay, so if we do that, okay, to two significant figures, we get a 4.7 times 10 to the, what do we got here? 1, 2, 3, 4, 5, 6, 7 newtons per coulomb. Pretty strong field. Okay, so that's our electric field strength there between those charges. Of course, you can have an example where you have to find something else involved in the example as well. Okay, you could have, given the electric field, you could find something else. So let's do one example of that before we shut her down. It's 35 minutes, so we'll go a little bit longer here. So let's say we have an electric field of around a point charge. Measures, let's say 5.6 times 10 to the 6 newtons per coulomb. That's times 10 to the 6. I'll fix that in a minute. At 0.55 meters away. 0.055 meters away from the charge. And the size of the point charge. Okay, so in this case, we should put this as an exponent here. Okay, so if we put that as an exponent, okay, so in this case, we have our electric field formula. Okay, KQ times R squared. So we want to solve for Q. So if we want to solve for Q, we're going to multiply by R squared. So it's going to be E times R squared equals KQ. So if we want to get the Q by itself, we divide by K. So Q then is going to equal ER squared over K. Okay, so we can plug our numbers into that. So our E value is 5.6 times 10 to the 6 newtons per coulomb. Our R value is 0.055 meters squared. And then we have to divide by 9.0 times 10 to the 9. What is it again? Newtons meters squared per coulomb squared. So the meters squared are going to cancel out, right? And then obviously the newtons are going to cancel out. And 1 coulomb is going to cancel out. So we're going to be left with a coulomb answer. Let's take our calculator out. 0.055 squared, right? Times 5.6, exponent, scientific exponent, 6, equal, divided by 9.0, exponent 9, and I get 1.9 times 10 to the 6 coulombs, or 1.9 micro coulombs. Okay, so probably what I'm going to do next day is put up some practice questions with electric fields, Coulomb's law, charging by induction and contact for practice before we go into our next area, which deals with potential difference or voltage, which in an electric field. Okay, so we'll stop there as we got into about 40 minutes, and that's long enough for today. Okay, so we'll see you tomorrow. Tomorrow will probably be a practice work period on some of this stuff.